Assalamualaikum, dear students. In this class, we will be discussing the concept of adjoint of a matrix. So, in the previous lecture, I have gone through minors and cofactors. Here in this lecture, we will define first of all the adjoint of a matrix. So, what is adjoint of a matrix? For example, you are given a matrix. For the given matrix, I'm talking about the square matrix. So if you are given a square matrix, for every element there is say cofactor. So we will find those cofactors. We will make a matrix of cofactors. So after making the matrix of cofactors, we will transpose that matrix of cofactors. The matrix so obtained is called as the adjoint of the matrix, given matrix. So once again, now we will define in the formal way. The adjoint of a square matrix is the matrix defined as the transpose of the matrix Aij, where this Aij of order n cross n is the matrix of cofactors. Okay, adjoint of a matrix A, it is usually denoted by ADJA. Okay, so this is any matrix, given matrix. We will find the transpose, or we will first of all find the cofactors of every element. So we will enlist them here. Then we will make the transpose of that matrix, transpose of the matrix of cofactors, this one. Okay. After that, we obtain this transpose of a matrix of cofactors. This transpose of matrix of cofactors obtained here, this is called as the adjoint of the matrix. Okay, so the definition is very simple. The only task that we have to do here is to find the cofactors of each element. Here are some definitions. Say here, for example, we have singular matrix. If you want to define a singular matrix, a matrix is said to be singular if its determinant. Everything what I'm talking is about the square matrix, because minors and cofactors are related to the square matrix. So a square matrix is said to be singular if its determinant is equal to 0. And if its determinant is not equal to 0, it is said to be non-singular matrix. Okay. We have some theorems here. Say theorem number first is, if A is any square matrix of order n, then A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. This identity is very beautiful, because you know that in matrices, the commutative law does not hold. Here you see the commutative law holds. It's one matrix A, adjoint of A is another matrix. You see A into adjoint A is equal to adjoint A into A, and their value is equal to determinant of A into I. So we can say like this: the commutative law of multiplication of matrices does not hold in general, but it holds here for the adjoint of a matrix. If we will multiply adjoint of a matrix to the given matrix, parent matrix, here the what I should say here, the commutative law of multiplication holds, and their product is equal to determinant of A into I, where I is this identity matrix of order n. Here is the verification for this. You can see it's very simple. Next theorem, that is, if A and B are two non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. Okay, A and B are non-singular, means their determinant is not equal to 0. So same is the case with AB, then determinant of AB is not equal to 0 and determinant of BA is not equal to 0. So it's not any hard task to do. Verification is very simple. So the next is, Here we have a remark that is taken from this very theorem, that is adjoint of A into A, that's equal to determinant of A into I. Determinant of A, if we will take now the determinant of adjoint of A into A, that is determinant of the right hand side, we will take a common, determinant of a common here, determinant of a common here, determinant of a common from the third row. It will be determinant of a cube, and it is identity matrix. You know the identity matrix has determinant equal to 1, so it is adjoint of a into a is equal to determinant of a cube. So we will apply here the theorem that determinant of a into b is equal to determinant of a into determinant of b. This is equal to determinant of a whole cube. So we get at the end determinant of adjoint of a is equal to determinant of a square. That means if we have a square matrix of order n, then determinant of adjoint of A is equal to determinant of A raised to power n minus 1. It's very important. Okay. Next is, this is theorem number 4. A square matrix is invertible if and only if A is non-singular matrix. For example, we have a matrix, square matrix, given square matrix. It's invertible, means its inverse exists only if and only if it is non-singular matrix. So for the singular matrices, this does not happen. So for non-singular matrices, we have this theorem, and its proof is very simple. You can see it here, and this is the conclusion. Inverse of the matrix A, square matrix, that's non-singular. Non-singular means this determinant should not be equal to 0. This is equal to inverse of the matrix is equal to 1 by determinant of A into adjoint of A. I hope that you got these results. These results are very important from the inverse point of view. If we want to find the inverse of a matrix, there are so many methods to find the inverse of a matrix, but this is also one of the important methods. Hope that you got it. Thank you for joining the class.